So exponential functions you should be familiar with from 9th grade or 8th grade. So an exponential function looks like a number that's the base and the variable is the power, right? So it's not a polynomial. Polynomials have a variable base and a numeric power. These are like reversed. The base is a number and the exponent is the variable. A has to be a number for exponential functions. A has to be a number greater than 0, so we can't have a negative base. Also, A can't be 1. Why can A not be 1? Yeah, if it was a base of 1, that's really just 1. So it's the constant function, y equals 1. So the base has to be a non-1 positive number. So here's a couple examples. So we have 2 to the power x, we have 1/2 to the power x, 1/2 to the power negative x, and 0.6 to the power x. So evaluating these is just a matter of, typing it in. A lot of times if it's not a whole number, you can't do it in your head. You just need to let your calculator crunch it. If it's a whole number that you're subbing in, then you probably could just do it in your head, depending on what the power is. So go ahead and evaluate these and see what you get. You actually have to whip out your calculator. Yep. Okay, are we okay evaluating? Peachy. Okay, graphs of exponential functions. You should have graphed these before. This is like a review of graphing these, right? Do you remember this shape? Yes? Yes. So it starts out like very low, right next to 0, but not quite 0, and then it grows exponentially, right? No, it is not a 1, 3, 5 thing. This one is base 2, so it's a 1, 2, 4, but that's because it's base 2. It's the growth rate of an exponential depends on the base. So the one right here that's shown has a base of 2. This is 1 times 2 to the 1x power. If I change the base, the curvature is going to change a little. So a higher base means that it's growing faster. It got like steeper, right? It's all about the base. It is. What if I made it 1? Getting closer. Whoops. Oh my gosh. Whoops. Oh my gosh. 1. So that's why we can't have base 1, because base 1 is not exponential, it's a constant. You asked a second ago, does it always go through the point 0, 1? And the answer to that question is sometimes. Sometimes it always goes through, and sometimes it doesn't. If you change these other values, like if we put a multiplier in the front, it might change what that number is. That's a vertical stretch. Or if you change the number in front of the, I don't know why it does that. It doesn't like being on a smart board. You can change the number like with the X in the top and it'll do that too. And then we could also shift it up or down. So all of those things are going to change what, that's just changing, it's a vertical translation. It's changing the location of the asymptote. Yep. Here's like the main characteristics of an exponential function. The domain is all real numbers, right? Every x value is fine. We can plug them all in. But the range is limited because of that horizontal asymptote. It's always above that, unless it's always below that. The intercept is 0, 1. And again, some translating this can change that. It's an increasing function. It never turns around and goes down. It's always just growing. The x-axis is a horizontal asymptote. We kind of talked about that. It has an asymptote at 0. And it is continuous. It doesn't have any breaks. You might see a fraction base and know that it's decaying, or you might see a greater than 1 number with a negative power that's also decaying. Another way to think about this negative power is that 3 to the power x would look like this. That negative power, you can think of it as a horizontal reflection, like it reflects it in the x direction around the y-axis. So if I have a graph of 2 to the x and I'm trying to match these, what is 2 to the x subtract 1? What's that going to do? That minus 1 is going to do what? Shift it down. So let's see if we can match it. Which one got moved down? That one, right? You can look for the sort of the asymptote to see if it moved down. The f is just like, for us, the f is that it's exponential, or maybe the f is that it's a square root. The f is the function. Okay, so if we have a negative in front, like think about if there's a negative in front of a parabola, what does it do? Yeah, reflects it vertically. So which one of those is reflected vertically? The first one. Here's our original. We reflected it down. Is that okay? Okay, you can think of this as a reflection left to right, or you can think of it as that we know that it's decaying now. So that's this one. And so this one, if it's with the x, it shifts it to the left or right. So this one is shifted to the right 2 units. You can see it goes through the point 1, 1 now. Used to go through the point 0, 1. It shifted it to the right by 1 unit. It's hard to see left-right shifts on these graphs. Right, but look at where the asymptote is. The asymptote did not change, so it didn't drop it down. It shifted it over. And that's why they're hard to see, is because like he's like, it looks like it dropped down by a half, but the asymptote didn't drop down, so it moved it to the right. Okay, let's sketch a graph. So we have the function f of x equals 2 to the power x plus 2 plus 3. So when you're graphing these, the first thing you want to do is sketch in your asymptote. Yep. Usually the asymptote is 0, so you're just looking for, did that thing shift up or down? So ours shifted up 3, so the asymptote is at y equals 3. Thank you. Beyond that, I would just sub in 2 or 3 x values to place it, especially if you have a left or right translation. What? It does, but people often make mistakes on these because of how they aren't. Like with the parabola, it's easy enough to be like, oh, the bottom moves left and right. With these, it's hard. I usually do try to pick the x value that makes the exponent 0. So I would pick x equals -2. Then f of -2 is 2 to the 0 power plus 3, which is 4. 2 to the 0 power is 1. So -2, 4. And then just pick another number. Maybe let's pick, well, that's not going to fit on our graph. Let's pick 0. That's a good number. I like 0. F of 0 is 2 squared plus 3, which is 7. Once you have 2 points, you can sketch it. There is no vertical asymptote. If you zoomed out and looked farther and farther to the right, it would just keep growing and growing and growing. Solving simple exponential equations. You know how our graphs are only increasing? They just grow or decay. They only go in one direction, okay? So what that means is exponential functions are one-to-one. Quadratics aren't one-to-one, right? If I have the same y value, it happens twice on the graph. But for exponentials, they are one-to-one. And so we can use this one-to-one property to solve simple exponential equations. Complicated exponential equations we have to solve not using this method. We'll learn another method for solving complicated ones. But for simple ones, we can use the fact that they're one-to-one. Yeah. One-to-one means that if you have two exponentials that are equal to each other with the same base, then their powers have to be the same. So I could use that to help me on this equation. I have 9 to the third power, I have 9 equals 3 to the power of x plus 1. Well, I can think of 9 as 3 to the power of 2. So this equation is the same as saying 3 squared is equal to 3 to the power x plus 1. Well, the only way that can be true is if the powers are equal to each other. So x has to be 1. But you have to think of how you could write this as the same base. So this one is a little trickier. So this is, I'm going to write this as 2 to the power of something. 2 to the power of negative x. And if I write this as 2 to a power, it's 2 to the power of 3. So negative x is 3, so x is negative 3. So this is a kind of slick way of solving exponential functions or exponential equations. It only works if you can think of that number as a power of the right base. So if we had like a 7 here, this method would not work, right? So for that, we'd have to have a different method. There's nothing to type in your calculator. What you should be testing in your calculator, if you want, is to do this and see if you get 8. Oh. Okay, there is a base that comes up a lot in math and science. It's the base E. E is an E because it's named after Euler. E is a number that's like pi. It's irrational. It's transcendental. You can't write it as a fraction. If you were able to expand the decimal of it, it would just go on and on forever and ever and ever. It does not. After that, it's different. It's not rational. It has no repetition. 2.71828, it does have like a 1828 again, but then it's different. It's like pi. It just goes on and on and on with random digits. So it's called the natural base. So this is called a natural exponential function. You can graph it the same way that you graph regular exponential functions. Decide where your asymptote is, plug in a couple of points, sketch it. You don't need to do anything fancy for this. Do you know where the base E is in your calculator, though? Because you will need to use that base. It's a second function. It's usually a second function of the natural log button. It's an L. It's an LN, yeah. So if you wanted to know what e to the negative 2 power is, you could type that in your calculator. Or if you wanted to know what e to the negative 1 power is, or e to the 0.25, go ahead and crunch all of those. Yeah, we'll use those log buttons after Thanksgiving. They do have to do with exponential functions. I love logs. I think they're really fun. Like, you wish you could do them more often because they're really great. And like, yeah. Rational functions. We wish we could do it more. These all look like really small numbers, but e can be big. Like if you did e to the 4th power, that's starting to get very big. 54. Those were just all small powers, but it does get big really fast. This is between 2 and 3. Okay, so we're going to do 2 quick application problems that have to do with exponentials. The first one has to do with earning interest on money in a bank account. So if you've taken financial lit or are taking financial lit, you've probably used some of these equations. But if you haven't, it's fine, like you will in the future. And the other one is radioactive decay. Did any of you take chemistry last year? Well, it doesn't have to be radioactive. We could do carbon decay or any other kind of decay. That just happens to be what we're doing. Okay, the formulas for compound interest are these two. This one is if your compounding is happening at set intervals per year. So, for example, my bank account compounds monthly. So I would use n equals 12 for monthly. Yeah. It could be daily, it could be yearly. If it was yearly, what would n be? Sorry, n is the number of times per year. N, yeah, for annual, n would be 1. For semi-annual, n would be 2. For monthly, n would be 12. Sometimes, for some accounts, they're compounded quarterly. My 401k is compounded quarterly. How many times a year is quarterly? 4. No, quarterly in a year means 4 times a year. So every 3 months, yeah. Oh my gosh, wow. Snap. If it's compounded continuously, which doesn't happen in bank accounts, but other things like in nature can be compounded continuously. It's instead of having this fractiony thing happen, it's a base e, and it has an r times t power. So that one you don't have n because it's being compounded of every second of every day. T is time. It's t years. And R is the annual interest rate or the growth rate, or it could be the decay rate if we do decay. So you've got those 2 formulas. So our question says if you're investing $12,000 at an annual rate of 3%, what's the balance after 5 years? If the interest is compounded, we're going to do quarterly first. So that means N is 4. So our balance, A stands for balance, like the balance in your account. They use an A because it stands for accumulated amount. Okay, so A is equal to, you have your principal first, that's the money you put into the account, 1 plus the rate. Don't put 3 for the rate. It's 3%, so you use 0.03. Over n, n is quarterly, so it's a 4. And then our power is 4 times the number of years, 5 years. Basically, the exponent is how many times are you compounding it. Well, we're compounding it 4 times a year for 5 years, so we're compounding it 20 times. And you can just type it in your calculator like that, especially if you have this calculator. If you have the little one, you got to be more careful with how you type it in. You have to be careful. He's just a little guy. He can do okay. You just have to be careful. Okay, if you got an error, let's figure out what your error is. I don't know. You know what? Like in theory, yes, but I think in finance you usually just round down. I don't know. Put whatever you want. That's a times. I knew it was a times. I was like, it's not plus. So what would change if it's monthly? Yeah, n equals 12. Everything else would stay the same. Oh, I haven't typed it yet. What?
The biggest financial lesson that my brother heard was because he borrowed money from me and I charged him monthly. And it was like 5%.
And it was compounding. Did you charge him 5% a month? That's an annual interest rate of 60%.
Yeah, so he learned he never borrowed money.
But that's actually not how like a bank would do it. If you were doing 5% interest with a bank, they would compound it monthly, but it would be a monthly interest rate of 5/12. Like you would divide the rate by 12.
Isn't there some like government programs that compound it monthly so it has huge interest rates that
I don't know. So, where? You got 0 as the answer?
Isn't the decimal
No?
I got 13933.
Yeah, you have to do both of the 12s. That's probably, you have to have both 12s. You just don't have enough zeros on this. Just times it by 10, and you have your answer. Oh, that'll do it. Any other like issues? Continuously is a separate formula. Continuously is when it has a base of E. So it's A is equal to the principal amount multiplied by E to the power of the rate multiplied by the time. There's no N. It's compounding every second of every day, yeah. Yeah, I mean, look, all these are the same amount of starting money. The only difference is how often you compound. There's not a huge difference. But over 5 years, it only made a $8 difference. That's enough for lots of chicken nuggets, really. I mean, $8 worth of chicken nuggets? I feel like that's a lot of chicken nuggets.
say if you use like the
Yes.
formula, but as like a safe line count.
Uh-huh.
Just imagine that like you started at 8. That's how much time that.
Oh, I know. That's why they tell you to start saving for retirement early, because the earlier you save, the longer it compounds. Makes a big difference. Okay, let's, because you have that one. You need to put, you have too many parentheses. So like, what you would want to do is just put the multiplication symbol between those, and then get rid of that. Like that. So that it knows that whole thing is the power. See? Okay, we've got our equation right here. This is about half-life of radioactive radium. It says the half-life is about 1,599 years. So what that means is that if you start with a certain amount of it, after 1,600 years, you only have half of it left. The rest of it has decayed. So then if you had another 1,599 years, it would be half again. So this is an exponential situation where you're timesing by halves. So it says that here's an equation for the quantity present after t years. So you're thinking about t, the t is divided by 1,599. You're basically figuring out what fraction of the half-life has passed. That's a 1/2 base with that power, and you times it by 25 for this. So our first question is like, what's the initial mass of radium that we had? So that is initial in word problems means time 0. It means the starting time. So we're just going to sub in 0 for t. So it's 25 times 1/2 to the 0 divided by 1,599 power. The power is 0. Half is raised to 0 power. That's 1. So the answer is 25. What's the units? Does it say grams somewhere? Oh, mass in grams. 25 grams. I'm like, I can't see a mass word anywhere. Okay, so we've got 25 grams to start with. So the next question is, how much of that is still present after 2,500 years? So that's going to be 25 times 1/2 to the power of 2,500 over 1,599. You might later in chemistry. Oh, you guys didn't do radioactive decay? Hey, fun tip. When I'm typing this into my calculator, I almost always just do 0.5 because it's easier to type. Just in case you were wondering. Like basically anytime I'm typing a half in a calculator, I do 0.5 because you did an error. It's not. It is 8.45. Did you get that? Okay. Does anybody have questions on that? Anybody questions on this? Okay, here's your assignment. I have it printed like the problems, but it's in your book. But here's the problems. The answers are, well, some of the answers are in the back of the book, but I'll get the answers on Canvas. But since it's a new unit, they're not there yet, but I'll get them there. If you're doing graphs and you want little graph papers, either this or the little tear-off ones, you can grab some. Mm-hmm. There's a couple that you need to graph, but you can grab those little coordinate planes if you want. I don't know. It seems very wasteful. Did I give one to everybody? It's 7 and 10. 13 through 16 is just matching. Was it a lot of work?